Welcome back, ladies and gentlemen. We are back into Chapter 5, Section 1 of Polynomial Functions for College Algebra. And this is the second part of a two-part video. And so we're picking up with turning points. So if we have a polynomial function and it has a particular degree, let's call it degree n, then the graph of the function has at most n minus 1 turning points. Second bullet point, if the graph of a polynomial function has n minus 1 turning points, then the degree of f is at least n. So what we want to look at is the turning point. So when a function turns, and as we take a look at some of this, just a quick items off on the side. If I have an x squared, then we know our graph looks like this. Okay? If we have x to the first, then our graph looks like this. So we know then that on the x squared, we have what the degree is 2. 2 minus 1 is 1. So at most, we have one turning point, and which we do on the quadratic. On x to the first then, 1 minus 1 is 0, so we have 0 turning points, and that's what this graph has. So it's a quick demonstration of what we have and what we see. The turning points and the degree are related to each other. Let's take a look at these particular graphs here. Which of the graphs in this figure, figure 13, could be the graph of a polynomial function? For those that could, list the real zeros and then state the least degree the polynomial could have. And for those that could not, let's say why not. So which of these are indeed polynomial functions, which are not? So if we go back and remember what makes a polynomial, or what does the graph of a polynomial function look like, two key characteristics. They have to be smooth and they have to be continuous. So on figure number 13, does look like, as we follow through, it's nice and smooth, but as we get over here about x equals -1, we see that we have a gap, okay? So this is not a polynomial, okay, because it has a gap. That means it's not continuous. Taking a look at example letter B here, looks like we are continuous as we follow through. We're also very smooth. So this one, yes, is a polynomial function. Where are the zeros of our function? Looks like our zeros of function are over here at -2. Let's get my negative in there. -2 looks like over here at 1 and then also at 2. Okay? So we have 3 zeros here in this particular graph. And then also we have, looks like, a turning point down here and a turning point up there. So we have 2 turning points. So when we take a look at what we said as far as our theorem for turning points, if the graph of polynomial is degree n, then the graph has at most n minus 1 turning points. So we have 2 turning points here. So that means we must at most be degree 3. Okay, so one more degree than the number of turning points would be a way to phrase that. So this could be at least here. Our least degree then would end up being then degree 3 because there are 2 turning points. When we take a look at letter C, okay, letter C has a problem here because we have a cusp. Okay, so it is not smooth. Therefore, it is not a polynomial. Then we take a look at letter D. Letter D does appear to be smooth and continuous. So yes, that one is a polynomial function. If we take a look at our zeros, looks like we have only 2. Looks like we're at -2 and +1. If we take a look at the number of turns, so we have a turn up here and a turn down there. Whoops. Let me go ahead and clean this up just a little bit. We have a turn here, and another turn. So we have 3 turns. So since we have 3 turns, the number, the least degree we could have is 1 more than that. And so that would be, least degree then would be 4 as our, I was going to say 4 turns, but it's not 4 turns. Our least degree then has to end up being 4 because there are 3 turning points. If we go back up, take a look at this again. Okay. If the graph polynomial has n minus 1 turning points, then the degree of f is at least n. So n minus 1 is the number of turning points. So if I go ahead and add 1 to the turns, okay, then I end up with my degree. So I want to go back and take a look at something that's going to preface this up for the end behavior of a graph. We've talked about it briefly, but I want to discuss then the end behavior of the graph. So we've seen this particular item before, x plus 1 quantity squared multiplied by x minus 2. If I go ahead and pull back up this particular item from Desmos, we had x plus 1 quantity squared multiplied by x minus 2, and we see where we have our zeros here. We have zeros at -1 and at 2. We had a low spot. This is where we were trying to figure out where our not our turning points, where the graph was crossing the x-axis, where it was below the axis, where it was above the axis, those sorts of things. We talk about multiplicity in this particular graph. One of the things I mentioned also is that it looks like on the ends as x cubed. So an odd function where the ends do the same, excuse me, the ends do the opposite items. So one end's going up, one end's going down. What I want to emphasize in this particular section of the next few minutes is because this is an x squared and multiplied by this other x, it's going to look like the x cubed at its end. So how do we show that? How are we going to show that overall? That's the thing we want to take a look at on this piece. So let's go ahead and expand this. So let's see, so then our f of x equals x plus 1 multiplied by x plus 1 multiplied by x minus 2. Further, these first two terms then would be x squared plus I'm going to have an x and then another x, so it's going to end up being 2x and then a plus 1. And we're going to again multiply by our x minus 2 out there off one side, so I'm going to multiply x squared times x is x cubed. X squared times minus 2 is minus 2x squared. Clean my writing up here. Then we're going to have the 2x times the x is 2x squared. Multiplied by the minus 2 is minus 4x. Then we'll have a plus x. Then we'll have a minus 2. So overall then we have x cubed. See, those x squareds disappear. Then we're left with minus 3x and then minus 2. So that is the expanded form of our particular function here. Now what I want to do is I want to factor out, okay? I want to factor out this leading term here, which is x cubed. So if I divide everything by x cubed, I get a 1, because 1 times x cubed then gives me back x cubed. Then if I go ahead and factor out x cubed from these others, really one way to think about this is dividing each of those by x cubed, okay? So as we take a look at that just a little bit further, this is x cubed times 1 minus 3 over x squared minus 2 over x cubed. So really all I did was I simplified this piece here. I further then want to take a look at this spot, okay? So let's take a look at this. As x goes to infinity, okay? So as x goes out to infinity, as x goes way out to the right, what happens to 1 minus 3x squared minus 2 over x cubed? So as x gets really, really big, this 1 stays as 1. This piece here, if I'm dividing by a very, very, very large number, this whole thing is going to end up going to 0. Okay? Think about it this way. If I have a candy bar and I split it between 2 people, then I get 1/2 the candy bar. If I split it between 3 people, I get a third. 4 people, I get a fourth. 5 people, I get a fifth. So the bigger that denominator, the smaller the piece I get. Eventually, our denominator gets so large that practically we're at 0. Same way with this one over here, practically at 0. So as x approaches infinity, okay, this whole piece in here goes towards 1. So we could say this, as x approaches, and it doesn't matter if we're going to positive or negative infinity, f of x is going to start acting like x cubed, which is overall, wasn't that just when we simplified it, just the leading item, the leading term, the highest agreed term that we had in here. Okay, and so that is one of our theorems that we have in algebra. Consider what happens for a larger value of x, either positive or negative, and the implication for the graph. That's what we just did. So as we get very, very large, all those other values beyond that first term end up going towards 0. So overall, what we say then is the end behavior of the graph of a polynomial function, f of x equals this whole thing, is going to be the same as the graph of just whatever its power function is. So if we forget about all the stuff back here at the end, our polynomial as far as the ends of the graph are going to look like what the power function is of the beginning of the graph. So that's what we're doing here. The ends of the graph of x plus 1 quantity squared times x minus 2, we previously graphed this. What the ends of the graph look like are just the x plus 1, or excuse me, the x squared times x, which is the x cubed, which is this piece. Okay. So one other item, just to verify that this is the same thing that we had looked at before, we had said that this was going to be x cubed, and then, let's see, minus 3x minus 2. So let me get this black function off here. The red and the blue here, the red and the blue end up being, if I go back and forth between these, end up being the exact same function. So they're right on top of each other. Okay. So this red function here is the same as this one. So this function here, x cubed minus 2, the ends of the graph look the same as just x cubed. So the ends of the graph are going to do the identical items. Okay. So that is a theorem. So now we can take a look at example number 8. Identifying the graph of a polynomial function, we say which graph could be the graph of x to the fourth plus ax cubed plus bx squared minus 5x minus 6. So since we don't know what those middle terms are, we don't know for sure how it's going to be turning specifically. But what we do know are some other interesting characteristics. We do know that this graph overall is going to function like x to the fourth. And if this is x to the fourth, it's going to function like, as far as the end behaviors, are going to act like the same as what an even-powered function with a positive leading coefficient will look like. So the even functions, the ends of the graph look the same. And if it's positive, it's going to go up. If it was negative, they'd both be going down. So overall then, letter D is out because those ends, the ends on that function, are both going in the downward direction. So that disqualifies it from the rest of that piece. Another item that we want to take a look at is what we take a look at back out here. The y-intercept is going to be negative 6, because if I plug 0 in for x, these first 3 terms, or 4 terms, all go to 0. The only thing we're left with is negative 6. So we know that we have to cross the y-axis at negative 6. So that takes letter A out because it's going to cross the y-axis at a positive. And B and C could be possibilities here because we don't have a scale. So we don't know, is this negative 6 or is this negative 6? We don't know overall, so we just have to take it as is. Either one of those could be potentials. When we take a look at the number of turns, because this is degree 4, there can be at most n minus 1 turns. So we could have at most 3 turns in this case. So let's see here, we have 1, 2, 3 turns on letter B. Got 1, 2, 3, 4, 5 turns on letter C. So since letter C has 5 turns, that's too many turns for what we could have. So as far as the options for us, letter B then is the only one that we could say could be a possibility for this particular graph. And you have some of these questions in homework as far as saying which of these things are possible. So you have to go through for the various components. Take a look at the end behavior, take a look at the number of turns, and take a look at the constant at the end as far as where would it cross the axis. And our last item for today is this particular video is finding a polynomial function from a graph. So let's reverse the whole thing here. So instead of being given the equation and being asked to graph it, now we're being told, hey, here's the graph. What was the original equation? So things to notice here, one of the things would be what are the x-intercepts? So the x-intercepts are at -2. We have another one here at 0. And we have another one here out at +2. Since those are the intercepts, let's see, we take a look at the multiplicities. The one here at -2, we turn here, so that's got a multiplicity of 2. So multiplicity of 2. At 0, we go through it, and at 2, we go through it. So both of these then, let's say, would have multiplicities of 1. Okay, so we're going to take the smallest. Now, theoretically, this 2 could be a multiplicity of 4, so it's got to be an even, and each of these other values where we cross have to have an odd multiplicity. We'll start with the smallest evens and odds typically that we work with are the 1 and the 2. Also then, based off our intercepts, then we know these are also the roots or the zeros of the function. So we can write these, remember, if f of r goes to 0, then x minus r is a factor in the overall polynomial. So we have x minus -2, and because that was an even multiplicity, we're going to put that square in there. Then x minus 0 for this one here, and then x minus 2 for this third one. Okay, and each of these technically have multiplicity 1, so we could put the 1 there. Generally, we don't write the 1s because that's just extra information. Oh, and then we could have a leading coefficient out front, so we don't know what that is yet, so we'll just call that a. So we got f of x equals a multiplied by x plus 2 quantity squared multiplied by x multiplied by x minus 2. As we try to finish this up and take a little closer look at this, we try to figure out, well, what's the value for a? So then what we need is another point on the graph, and that's where this -1,6 comes in. Okay, because if this is -1,6, then we're saying f of -1 equals 6. So if that's the case, then f of -1 is the same as 6, which is the rest of this evaluated when x is -1. So -1 plus 2 squared multiplied by -1 multiplied by -1 minus 2. So now I'm going to go ahead and simplify the right side so I can figure out what my a value is. So 6 is going to be a multiplied by, let's see, 2 plus -1 is 1 squared is 1, multiplied by -1 multiplied by -3. So double negative in there turns positive, so 6 equals a multiplied by 3. That means a must have been 2. If that's the case, then I can rewrite this and make it f of x equals 2 multiplied by x plus 2 squared multiplied by x multiplied by x minus 2. So this is my polynomial overall that matches with that particular graph. Now, one of the things that we'll need to do for our homework additionally is to expand this all out. Okay. Now, overall, we see that we have 1, 2, 3 terms. So what we anticipate then is we anticipate this to be degree 4. Let's go ahead and expand this out and verify that that is what we end up with. So I'm going to go ahead and rewrite this a little bit. So I'm going to put this x out front, and then the x minus 2, then this x plus 2 multiplied by x plus 2 in the rear. The reason I'm doing that is I'm going to distribute this first piece. So that's going to be 2x cubed minus 2x, multiplied then by this last piece. So I'm going to expand these also. So x squared, x times x, and I get 2 x's and another 2x. That's going to be plus 4x. Then I have 2 times 2 is going to be 4. Now I can go ahead and expand the rest of this. And let's see what we end up with. I made a minor mistake here because it's 2x times x should have been 2x squared. I noticed that when I started multiplying, so I was going to end up with an x to the 5th term as an x to the 4th, and I know it should have been an x to the 4th overall. So let's take a look at this. So 2x squared times x squared is 2x to the 4th. 2x squared times 4x is 8x cubed. Then we have plus 8x squared. Multiply the 2x here, so it's going to be minus 2x cubed. So I'm going to head, instead of writing these all horizontally, I'm going to write these underneath their like terms. 2x times plus 4x is minus 8x squared. That's convenient because those cancel. And then we end up with a minus 8x. So as I expand this, what we end up with is 2x to the fourth. Then we have plus 6x cubed. And then I end up with a minus 8x. Okay. So as we take a look at that and just verify what we end up with, let's see, make sure I didn't make any mistakes in here. So 2 times the x is 2x, and then multiply x minus 2, 2x squared. Oops, I did make a mistake. This should have been a 4x. Okay, minor mistake here. So that should have been a 4x. So that's going to change this bottom row down here. All right. So go back and every once in a while just double check things just to see that things make sense. This one, minor mistake. So let's see. So that's a minus 8x cubed. Minus 4. I'm sorry. Minus 4x cubed. So I was doing that 4 times the 2. 4 times this is 4x cubed minus 16x squared, and then minus 16x. All right, so let's go back and correct the rest of this. So 2x to the fourth, and then we're going to end up with plus 4x cubed, a minus 8x squared, and then a minus 16x. All right. So I think that looks about right then as far as what our polynomial was. And we see that we have a degree 4, so it should be at most 3 terms. And we have our coefficient at the end, or constant at the end rather, is a plus 0. Let's see if that matches up with our graph. Okay, so we've got at most 3 terms, so 1, 2, 3 matches, and we cross at 0. In this case 0, 0, which is what we anticipated as well. So then we ended up with, overall, we did end up with the equation for our polynomial. So summarizing the whole of chapter 5, section 1, the graph of the polynomial function. And again, we have this really long looking setup, but if we remember, this is just a number. So the number associated with x to the nth power, a number associated with x to the n minus 1 power. So maybe this is x to the fifth, and x to the fourth, x cubed, x squared, x to the first, and just a constant. The domain was a set of all real numbers. The degree is what the highest exponent is. The y-intercept is out here at a sub 0. Because it's a polynomial, we do have to be smooth and continuous. The maximum number of turning points is the degree minus 1. If we have an even multiplicity, we touch the x-axis and then turn at the axis. If it's an odd multiplicity, the graph crosses the x-axis. Between the real zeros, the graph either has to be above or below the axis because we can't cross. And for the end behavior for large values of x, and in this case, our probably should put absolute value of x, is it doesn't matter if we're going towards positive infinity or negative infinity. The graph is going to look like the power function of just whatever that first term was going to be if we're in standard form. So this a sub n x to the n is what our graph is going to look like overall. All right, so we did it. We finished up chapter 5, section 1, all on the graphs of polynomials. And again, if you found a mistake, please let me know. Otherwise, we'll see you in another video.